Hello, Professor.
Hi, Alpha. How are you?
Doing all right.
I'm good. So, what's your question? Let's get started. Let me see if
Okay.
this is in focus first, okay?
Okay.
How does that look? Is that look in focus?
Yep.
Okay, great. What can I do for you?
Okay. I was actually want to ask about number 8 on the test review. Did you guys
Oh,
already cover that, or?
no, I don't think so.
Okay, great.
That's one of the set equalities, correct?
Yes, number 8 on the test review. Yes, it's the mathematical induction to
Induction,
prove P of
sure.
n below. Yeah.
Let's do it. So we're going to prove that the sum from I equals 1 to n of the expression 4i cubed is equal to n squared times n plus 1 squared for n greater than or equal to 1. Okay, so what's our n naught?
Our n naught is n should
What's
be.
our lowest level value for n?
Oh, yeah, it should be 1.
That's right. So our n naught is 1. So we'll prove our basis for 1. Okay,
Okay.
so let's prove our basis step. We're going to just tell our reader, let n naught equal 1. And what do we wish to show?
Wish to show that that P of 1 is true.
That's right, because this statement, you know, is P of n.
Yes.
Okay. So I guess I should have said proof by the PMI.
Yeah, the principle of mathematical induction.
Let P of n be above.
Okay.
Okay. So we're going to prove that P of 1 is true. And we're going to very carefully deal with the left-hand side separately from the right-hand side. Okay.
Okay.
Left-hand side and the right-hand side. Okay. So the left-hand side of P of 1 is, will you help me? Everywhere we see an N, we're going to put a 1, right?
Okay.
So tell me what we're going to write.
Must be
The
sum.
sum
Yeah, sum of I equals 1 over 1.
to 1.
Yeah, 2. Yeah, 2 1.
Uh-huh. Uh-huh.
And 4i cubed.
Great. So that's going to be a single term, isn't it? Where I has the value 1. So what will that be?
So that should be 4 times 1 cubed.
And that's just 4 times 1 or 4, right? So the left-hand side of P of 1 is 4. Let's check out the right-hand side of P of 1. We always look at the left-hand side separately from the right-hand side.
Yes.
So what is the right-hand side of P of 1?
It should be 1 squared times 1 plus 1 squared.
So it's 1 times 2 squared, right? So it's 1 times 4. And that is also 4. Great. So the left-hand side equals the right-hand side, and P of 1 is true.
Uh-huh.
What do we do next?
Did you guys go over 6 yesterday?
Well, we haven't finished this proof.
Oh, we haven't
That's
finished
only
it,
the
right?
basis step. We've got to do the inductive step, the
Yeah, I
assume
forgot.
P of K and prove P of K plus 1. So let's work
Okay,
on the induction step or the inductive step. Now we need a K. So we're going to tell the reader what K is. We always can start the basis step by telling the reader what the integer in naught is, and we start the inductive step by telling the reader what K is. Let K be an integer, all right? Where K, let's tell the reader where K starts. What is the range for K?
K should be less than or equal to 1,
Greater than or equal to 1.
or greater than or equal to 1, sorry.
All right, so what do we assume in the inductive step?
We assume that K,
P of K
yeah, P of K, okay.
is true. So what we're doing is we're assuming that we're standing on this step and that P of K is true. And what we want to show, our wish, is to show that we can step up and get P of K plus 1 true. Okay?
Yes,
But let's write P of K down. Let's write it explicitly
okay.
because we need to see what our inductive hypothesis is because we're going to need to use it later. So we look at P of N, and everywhere there's an N, what do we put?
Okay,
Correct. So tell me what to write.
so we put sum of I equals 1 to K
Uh-huh.
for I cubed equals K squared times K plus 1 squared.
Okay. Now that is our proof money. Let's put a box around it so that we can find it later when we need it. This is our inductive hypothesis. And when we use this, we say by induction. All right, now let's take a look at our wish. We want to step up. So what do we wish to show?
We wish to show P of K B plus 1, yeah, is
It's
true.
good. And let's write that explicitly, because if we don't know what we're trying to prove, we won't be able to prove it. So everywhere we see a K, now we're going to put a K plus 1.
Okay,
Here we go. It's going to be the sum. This
yeah,
is
the
our
sum
wish.
of I equals 1 to K plus 1
Good,
for I cubed
good.
equals K plus 1 squared.
And we have to use parentheses because now we're substituting in a binomial. See how this has two parts?
Yeah,
For the monomial K, we're substituting K plus 1. Good. And then times.
yeah, K plus 1 squared.
Great. In other words, we're trying to get it to look like K plus 1 squared times K plus 2 squared. And this is our wish, okay? So
Okay,
I'm just going to put my little dreamy wish cloud around it so I don't accidentally think I can start with this because we cannot. It is a wish.
yes,
But we do have this in our hand to work with as our inductive hypothesis. Hey, Jessica, we're proving problem number 8. It's the induction proof on the test 3 review sheet, okay? So we're just starting in on the inductive step where we're going to let K be an integer, where K is greater than or equal to 1 because our N naught was 1. And we assumed P of K is true. So this is the statement P of K. We just looked at P of N, and everywhere there was an N, we put a K. And now our wish is to show P of K plus 1 is true. Everywhere there was a k before, we replace it with a k plus 1. And of course, k plus 1 is k plus 2. All right, so here we go. We're going to tell the reader what we're doing. We're going to be starting with this left-hand side of p of k plus 1, and we're going to work on it until we get it looking like the right-hand side. So starting with the left-hand side of p of k plus 1, right? We have, well, let's just write it down. It's the sum from I equals 1 to k plus 1 of 4i cubed, right? So what is the big tool that we have learned that helps us break this down so that we can use our inductive hypothesis? It's always the same with these sum and product formulas. We want to break down the sum from I equals 1 to k plus 1 of the expression to a sum from I equals 1 to k of that expression. So we can use this equation plus the leftover.
Okay.
So this really is
Yeah, so it's the sum of k, yeah, I equals 1 over k.
2k. You're starting at 1 and going to k. Of 4i
2k.
cubed. Yeah, not TWO, but TO, like going to K, starting at I equals 1 and going all the way up to K. That's
Yeah.
why we say from I equals 1 to K. And then we've broken off the K plus first term. So it starts at K plus, I starts at K plus 1 and ends at K plus 1. It's just that single broken off term where I is going to take on this value K plus 1, okay?
Yes.
So do you remember how this sum is equal to this sum plus this sum?
Yes.
Does it make sense?
Yes.
All right, great. So now the reason we did that, hey Karen, is that it puts us in a position to use our inductive hypothesis, doesn't it?
Yeah.
So what should we do now? In fact, you can kind of put a green box around this just to kind of show yourself, ooh, I'm seeing this here. And I know it's equal to that. See what I mean? So what should we put in?
She could put in, or she put in what we selected.
Well,
Yes.
you see how we have the left-hand side? See, this is P of K right here. It has a left-hand side that is equal to its right-hand side. This we have assumed. We have this money in the bank. We get to
Okay.
use this. So now we've broken this sum that started at I and ended at K plus 1 of 4i cubed into two pieces, a big piece, which is the first I equals 1 to K terms, 4i cubed terms, plus this single broken off term. Why did we do that? We did that because now we can use this. We know this is equal to that. So we can make a substitution for this with that. That was the whole point.
Okay.
You see it?
Yes.
So this is k squared times k plus 1 squared. And the minute that we do that, we are going to tell the reader, hey, we just used our inductive hypothesis. We always do that. Don't lose a point and forget to do that. So that takes care of the green box portion. But we still have this broken off term, don't we?
Yes.
And we need to evaluate that, right? And we can, rewrite it here just so when you look at these notes, you understand that the induction isn't evaluating this. We can do that in the next step. So we have k squared times k plus 1 quantity squared. And now what is this term?
That becomes a k.
Okay, look at I.
Yeah, the I. Yeah, that
What
becomes
what is I's value in this broken off term?
it's k plus 1. So
So
the I becomes k plus 1.
that's right. So it's 4 times the quantity k plus 1 squared.
Okay.
Oh, oops. I think it's cubed, isn't it?
Yeah.
All right, great. So we've used our inductive hypothesis. We started with the left-hand side of P of k plus 1. We broke it up so that we could use that inductive hypothesis, and we had this broken off term. And now we're working to get to this. All right, so let's keep our eye on the prize. We are trying to get this expression to look like k plus 1 squared times k plus 1 squared, but that's really just k plus 2 quantity squared. Do you agree?
Yeah.
And we can let what we're shooting for guide our next algebra step. Do you see how this is a product? There's no, and this is a sum. It's got, a product plus another product. But what we really want is just something squared times something squared. Do you see that? We can use that to guide us. We know we're going to need a factor of k plus 1 squared. Do you see a factor of k plus 1 squared here?
Yeah.
I do too. Do you see a factor of k plus 1 squared here?
Yes.
In fact, we've got 3 k plus 1's factors,
Yeah.
don't we? So
Yeah.
when we factor out the k plus 1 squared from here, what is left over?
Just k plus 1 squared.
No, we're pulling the k plus 1
Oh,
squared out front. What's left when we factor k plus 1 squared out of this first expression?
so it's just k plus 1 then.
I think it's just a k squared, because this is really k squared times k plus 1 squared. If we factor out the k plus 1 squared, we're left with k squared. Okay?
Okay. All right.
But you're right. Over here on this side, when we factor out 2 of these k plus 1's, we will have k plus 1 left, but we also have the 4.
Okay.
Well, that means we have k plus 1 squared times k squared plus 4 times the quantity k plus 1. Well, isn't that 4k plus 4 when we distribute the 4 across that? It is. And listen, I'm just sneaking a peek at what we want. I know we've got the k plus 1 squared pulled out. I know this better turn out to be k plus 2 squared. And of course, k squared plus 4k plus 4 does factor. It is k plus 2 squared,
Okay.
which is the right-hand side of p of k plus 1. So in fact, p of k implies p of k plus 1, and now we just invoke the PMI. By the PMI, we can see p of n is true for all n greater than or equal to, where did we start? Well,
We started with n greater than or equal to 1.
that's right, and that finishes that. Now, let's just say that your algebra, isn't that great, but that you do know enough to recognize P of n and realize P of k is going to look like P of n, just with a k everywhere that there used to be an n. All right, so you can write P of k. And then let's just say that you understand that P of k plus 1 is going to look like P of k, except you're going to put a k plus 1 everywhere there used to be a k. K plus 1 becomes k plus 1 plus 1. And it's squared, of course. You should be able to start with the left-hand side. This doesn't take any algebra. That was just substitution. So that's nothing deep going on, but it is an important way to earn a lot of points. Be able to write your correct inductive hypothesis, be able to write your correct wish. Start, if it's a formula, start with the left-hand side of the formula you're trying to prove in your wish. Be able to break off that k plus first term. Realize that the reason you did that was to be able to make the inductive substitution using your hypothesis. That was the whole point of breaking off that term. And then be able to at least substitute k plus 1 in for I to get that broken off term evaluated. Now let's just say you can get that far, but you're having a hard time getting to k plus 1 squared times k plus 2 squared. That's the algebra part, right? So
Yeah.
you could just, let's say you get this far. Then you can just say, gosh, Dr. Good, algebra, yikes, you know, and then you can at least say, I know I want this, right? Because if you can write P of k plus 1, you should be able to know what the right-hand side of P of k plus 1 looks like. You should at least know this is what you're trying to get.
Mhm.
So you should be able to make your inductive substitution and evaluate that k plus first term, even if you can't do the algebra to get the right-hand side. You're going to get most of your points, and you still can write, hey, by the PMI, we can see P of n is true. So always get your point for invoking the PMI, even if you couldn't perfectly do the algebra. And tell me what you wish to get, even if you can't, get from point A to point B yourself, you're only going to lose at most like 4 points out of a 20-point question.
Okay.
Okay? So maximize your points by at least understanding the process. Does that make sense?
Yes.
Okay, good. Jessica, you joined us next after Alpha. What's your question tonight?
I was just gonna see if you could just kind of just go through some more, I guess just some hard questions that you've seen other students deal with, and just I was just gonna kind of like just test myself, or we can just kind of work on it as a group to see if we can kind of do it on our own more so instead of you giving examples.
Well, I'll tell you what, if you want some do laters, Jessica,
Mm-hmm.
weren't you in office hours?
Yeah, I have the do laters that you had gave.
Did you do them?
Not all of them yet.
Uh-huh. Well, I would start with those.
Mm-hmm.
And I gave a bunch of do laters when we were in office hours uh, over the weekend. I gave a big page of do laters uh, from our pop-up office hour. I don't know if this was Friday or Sunday. And so there's a bunch there.
Okay, so just work over those due laters and just the one from class notes and whatnot and just
I mean,
use that.
there's so many of them. Yeah. I
I
mean,
know I was saying
and
there's a lot of
and I
them.
gave some more do laters in another office hour over the weekend. We had an office hour on May 1st, and then we had another office hour on yesterday. And there's bunches of do laters. Okay, so if you want to get together with people, then do use your contact information, email people, and see if anybody wants to get together in Zoom or something. And if you want to workshop together or get on campus and find people, we did that at the beginning of the semester where we organized groups and everybody got contact information. I would hope that you still have some of that. I think you can find a list of the emails in Blackboard. All right. Since you don't have a specific question, Jessica, Karen, do you have a specific question? You were the next one in the room.
As for me, um, I know, I mean, most of them are office hours, so I did do exercise the and choose R for, I think it's number six. Let me see. No, not number six. And I think it's number four.
Yeah, we haven't done that one yet. Do you want to work on that one? Shall we do number 4?
Yes,
Or
because
did you do it?
I already did B. B was easy to do, but it's just A and C. I mean, in the place in the algebra where you have to like factor, I didn't know how to do it with A and C. But B I already done do it. I just followed the formula. But A and C, I don't understand.
Well, that's understandable. All right, let's look at A. And this is just factorial. This isn't even in choose R. This is just practice with factorial, just to kind of set you up. Just like if you look at the class notes, the day that we covered in choose R, the do now in the class notes was just a warm up where we reviewed what we had already learned about factorial the day before. And I was just trying to warm you up for in choose R. So let's just remember how factorial works. If we draw a number line, we can understand what's going on. So the n plus 2 is the biggest integer. What's the integer right before n plus 2?
N plus one.
Good. And what's the integer before that?
N.
What's the integer before that?
Negative N minus one.
Nice. N minus 1. This will be
Mm,
okay. So the
okay.
point is n plus 2 factorial is n plus 2 times n plus 1 times n minus 1 times n minus 2. Keep going, till you get down to 3, 2, 1, right? And n plus 2 factorial has more factors than n minus 1 factorial because n minus 1 factorial is just n minus 1 times n minus 2, right? Times n minus 3. Keep on going until you get down to 3, 2, 1, right?
What?
So n plus 2 factorial, we can write it as n plus 2 times the integer before n plus 1 times the integer before that, n times the integer before that, n minus 1. And instead of writing all the rest of the ones down to 3 times 2 times 1, we can just put the factorial there because that's what n minus 1 factorial means. It means n minus 1 times n minus 2 times n minus 3, keep going, right? So when we have n plus 2 factorial divided by n minus 1 factorial, well, this is just the n minus 1 factorial part. And these are,
Cancel each other.
yeah. And so the answer is just n plus
And
2 times n plus 1 times n. And that's it. You don't even multiply it out. Don't even bother.
okay, okay,
Okay.
okay, okay.
Now you said you know how to do B.
Yeah, I know how to do B.
Okay, good. Let's look at C then, because C is more general, but it's the same idea. It's in choose n minus 2. Okay, so we're going to use the same principle. We can still use this number line, but we need the formula. We have to recall the
And
formula.
choose R.
Yeah, right. Let's write the formula down here. N choose R
R equals
is
N factorial minus R. No. Over R. N minus
R
R.
factorial.
R.
Everything's factorial
Okay. N
times.
minus R factorial.
That's right. That's the formula. So here, The n is on top, but our r is n minus 2. So on the top, we have n factorial, right? On the bottom, our r is n minus 2. So it's r factorial is n minus 2 quantity factorial. That's our r factorial, right?
Factorial.
Right? And then we need n minus r factorial. So it's n minus the quantity
N minus 2.
factorial.
2 factorial
It's n factorial on top, and this
plus
is
n.
n minus 2 factorial. And then what is this? N minus n, and then minus a minus 2.
Wait, what's the wait, let me zoom in onto your thing. I can't see you wrote n minus 2. How did we go from n minus 2 n factorial n minus, how did you simplify uh
I haven't simplified this yet.
oh, okay.
But
Oh,
look, isn't the r n minus 2 here?
yeah, n minus 2 r, yes.
So the formula says n factorial on top. Okay, n factorial on top. On the bottom is r factorial. But this r is n minus 2. So instead of r factorial, it's n minus 2
Minus
factorial
2.
because r is n minus 2.
Yeah.
And then the n minus r quantity factorial, it's n minus, this is our r.
So how do we simplify that? I look
Well,
at it maybe like
what's n minus n?
0.
Good. And what's negative minus 2 or minus negative 2? See, because this minus distributes across this binomial.
2
So
n.
no, n minus n, the n's cancel.
0, 0 minus 2, 0,
No,
negative 2,
it's negative negative 2. This is
2.
n minus n plus 2. Like if you distribute the minus across the parentheses, because it's minus all of r. So r is n minus 2. So you've got to take this minus sign and it's got to distribute across all of r. So minus n is minus n, minus a negative 2 is plus 2. See? The n's cancel. N minus n is 0. But the negative, the minus a negative 2, that's going to become the positive 2. Does that make sense? So
I
this is 2 factorial.
2. Okay.
Want me to give you a do later? Well, we're not quite done with it because we're supposed to now use, information like this that we learned to simplify this a little further. Let's keep going.
No, that's okay. I just needed a review on this because I want to go back and work on my proofs. So I just needed a quick review on this for other material.
Well, okay, I just want to finish it though,
Okay.
because I don't want people to think that we're done. We're not. It's n factorial over n minus 2 factorial times 2 factorial. So it's n times n minus 1 times n minus 2 factorial over n minus 2 factorial times 2 factorial. The n minus 2 factorials cancel. 2 factorial is just 2, so it's n times n minus 1 over 2. Well, I just wanted people to see that, but that's actually the whole answer.
Okay, that works. That helped when you did the graph. When you do the graph, I always get the 1, 2, 3 negative. Anytime you do the graph, I'll always understand the problem.
Then do it for yourself.
Yeah, I have to start thinking like that. it's not the first thing that comes to my brain. I think about the formula directly. I don't think about the graph. So yeah. But
But
yeah.
sometimes it's hard to understand what this means unless you see the picture.
Yeah.
Good, I'm glad that helps you.
Mm-hmm.
All right, Cayenne, you're in the room. It's your turn. What would you like to work on? You have a problem that you'd like to have work? Cayenne, are you with us?
Yeah, I'm here.
Hey, how are
Don't worry. Let me
you? Good.
see. I
You've
was
graced us with your
let me
presence.
see. Yeah, I'm trying to. I don't know what when you've already gone through in the other office hours. I still need to go back and look at those. But I'm just going through
Well,
the
we
review
went
right now.
through, yeah, I can tell you which ones are done over the weekend and over the last, since it's been posted.
Okay.
Um, I can tell you by looking at it. I'll share the screen. Oh yeah, and the quiz 5 solutions are posted too, people. All right. We did problem 1 yesterday. We did part A, we did part B, and for the people that were in the room, I asked them to please work on C because it's alternating. We did not do C. We definitely did 2 several days ago. I think we did 2 on May 1st. We did 3. I can't remember which day. It was either May 1st or May 3rd because we had office hour May 1st and Friday, May 1st, and we had an office hour yesterday, May 3rd. I've been really piling up the office hours, so we did 3. We just now did 4. We definitely did 5. We didn't do part C, but if you listen to the video and think about it, then you should be able to do part C. We did number 6 on May 1st. We did number 7 yesterday on May 3rd. We just did number 8. We have not done number 9. Number 10 is posted because that is the quiz, take-home quiz 5, problem number 2. So that solution is typed up, and just look in the quizzes folder and you can find that. We did one direction of this equality in class notes, but it is a set equality. So the only thing we haven't done is the other subset inclusion direction of this set equality. Shall we work on that, folks?
Yeah, sounds good.
Okay. Okay, so I'm just going to write a few things and then I'll be able to close the window down. So problem 9, we're going to prove that A union B minus A intersect B equals A minus B union B minus A. All right. Now, there's 2 to prove, just recall, to prove X is equal to Y, where X and Y are sets. We have 2 things to do. 1, you have to show that X is a subset of Y. 2, you turn around and you show that Y is a subset of X. So it's 2 subset inclusion arguments to prove set equality, okay? So in this proof, we're going to let A, B, and C be sets. We need to show 2 things. A union B minus A intersect B is a subset of A minus B union B minus A. That's one. And then we have to turn around and show that A minus B union B minus A is a subset of A union B minus A intersect B. Now, we proved one of these in class. Does anybody remember which one we proved in class? Let's look at class notes.
Wasn't it
it's
in
the,
day 22?
yeah,
Thank you. Let's look in day 22. Now, we did functions on day 22. Oh, but wait a minute. Maybe it was our do now. Maybe it was our warm up.
Yeah.
Yeah, good call, Jessica. So we prove that A union B minus A intersect B is a subset of A minus. So we proved that direction, okay? And it's all there. Okay, it's all there. So let's prove the other one. Okay, we're going to prove two. So see day 22, do now for one, prove. We will do two. All right. So let's just remember what it looks like to prove subset inclusion. The general strategy, it's called an element chasing argument. We literally take an element from the set that's the smaller set, the one that we want to prove is the subset, and we chase it into the bigger set called the superset. All right, so let's let, I'll just call it X, be an element of A minus B union B minus A. That's the hypothesis to prove two, okay? We take an X in here. We wish to show that X is an element of A union B minus A intersect B. Okay? So that's the first thing you need to understand when we're proving subset inclusion, is that to do it properly, you take an element X from the set that's the subset, and you wish to show the element lives in the superset. Because the definition of subset is if X is in A minus B union B minus A, then X has to be in A union B minus A intersect B. So the second thing to understand, the major two concepts, I already told you the first one, is when we try to understand what it means for X to be in this compound set, A minus B union B minus A, we need to break down this set in the opposite order that we would build it up. Like if we were building this set, we would first build A minus B and B minus A, and after they were built, then we would take the union of that and find the final answer, right? That's if you're building the set. But if we want to understand what it means to be an element of the set, we're deconstructing the set, and we do that in the opposite order. Start with the last operator first. We break down the union first. So, by definition of union, does anybody know what the union operator for sets tells us? What do we
Yes.
know?
That is or.
It's an or. So X is an element of A minus B, or use complete statements. X is an element of B minus A. Don't just say A minus B or B minus A. Make these complete statements. Why? Because then you're going to be set up with the complete hypothesis for each of your two cases. You already have that work done. This or means cases, or always means cases. So case one will be what happens when X happens to be in this union by virtue of X being an element of A minus B. Case two will be what happens when X is an element of B minus A, because it's in one or the other. We just don't know which. In both cases, we have the same wish. Just like when we were playing cases with the QR theorem, we have the same wish. So let's actually just expound on our wish to make sure we understand it. We're going to break this wish down the same way we break down what it meant for X to be in this union. To understand this wish, we need to understand what it means to be in this compound set. What is the big operator, the last operator that operates in this wish set? Anybody?
It is and, the and operator in A intercept B.
Okay, so if we read left to right, we see union,
Oh,
set
minus.
minus, intersection, but that's not the sense of order of operations when there are parentheses. I'm talking about what is the last operator that operates if we were trying to build this set? Wouldn't we first build A union B and figure out what that is? And then we would construct A intersect B and get it all sorted. And then the last thing we would do would be subtract A intersect B from A union B. See what I mean?
Yeah, okay.
So when I say the last operator, I don't mean if we're reading linearly, I mean in terms of the set operation order. The set difference would be the last operator that would operate if you were actually constructing the set. Do you agree?
Yeah, I always get that confused. Sorry.
Well, but doesn't it make sense to build this stuff inside parentheses first and then operate on whatever those results are last?
Yeah, because, PEMDAS and all that.
Well, you were willing to speak up, so good for you. Now, maybe this will stick. We're going to break down what it means for X to be in this compound set by first attacking this last operator. See, we break it down in the opposite order that we would build it. So we're going to break down set difference. So what do we really wish to show? Well, we wish to show X is in A union. I'll just rewrite it here so we can see it. A union B minus A intersect B, i.e., that X is an element of A union B. What's the definition of set difference?
It's an element of A union B, but X is not an element of A intercept B.
Perfect. But X is not an element of A intersect B. And having that wish crystallized, and I'm just going to put my little wishy
I have a
cloud around.
question also.
Okay, let me finish my statement and I will let you speak. I'm going to put my wishy clouds around these. This is an and. Just because I don't want to accidentally think I have these in my hand. No, no, no. Our wish is to show both of these because once we have both of these with an and, then we can jump right to the real wish. Question.
As you were going through it, I was trying to work through it on my own and based off the class notes, and I have the we wish to show X belongs to A union B and X does not belong to A intersects B, because that's
That's
kind of
right.
how the class notes had it. If we had
That's
that,
right.
that's fine.
That's right. Yeah, that's fine.
Okay, I just didn't know if you wanted us to have the line before the IE and the after. If we
Oh,
would lose
don't even
point.
worry about that. Don't even worry about it.
Okay.
That's nothing important. The
Okay.
important thing is that you understand how to break
Yeah.
this set down in your wish, that you do understand it's a wish, and that you understand the definition of all these operators. First and foremost, set difference. And it sounds like you've got those down.
Mm-hmm. Okay. Thank you.
That was a good question. So now, folks, we're going to move forward to try to get to our wish. So now we have to back up and we have to deal with these cases. So case one, is that X is in A minus B. So let's suppose X is an element of A minus B. It's the same wish in both cases, okay? So we got to get X in A union B, and we are going to have to get X is not in A intersect B. Is everybody with me?
Yeah, so I just have a question. So from
Mm.
suppose X belongs to A minus B, are we gonna say by the definition of set diff, what we wrote in our wish?
Yeah, let's break this down. What does it mean that X is in A minus B?
X is in A and is not in B.
Yep, and now we've broken down this information in this case as far as we can. These are atomic statements, right? We can't break these down anymore. Once we've broken down our hypothesis, now we're going to try to build up from this to these, and then we'll get to that in one step once we have these. So how are we going to be able to get that X is an element of A union B when this is what we've got? We've got X is in A, and we've got that X is not in B.
By the definition of union?
Yeah, since X is an element of A, we know X is an element of A union B because that's the OR operator. If X is in A, then it's certainly in A or in B, right? By definition of, I'll just say union. So we've got X in A union B. Great, we're halfway home. Now we need to get that X is not in A intersect B. How are we going to do that?
Is it case two?
No, we're still in case one. We're going to have to do this both in case one, and we're going to have to turn around and do this. See, we have to get this entire wish in both case one, and then we'll also have to get the entire
Definition
wish.
definition of intersect?
Okay, so what are we using that we have to get this?
Oh, X is not in B, but it's in A.
Well, don't even bother to say it's an A. That doesn't help us. The
Oh,
point is, since X is not in B, it can't be in both, can it? Because it's not in B. So X is not in A intersect B, because to be in the intersection, X would have to be in both. Just mention the part that's pertinent. See what I mean? Like X was in A and X is not in B, but we didn't mention that X was not in B when we talked about why X is in A union B. It doesn't make sense, right? To kind of hurt
mm,
yourself. All we needed was to say, but X is in A, so we get it in A union B. Oh, well, X is not in B, so X can't be in both A and B. So X is not in A intersect B. See what I mean? Only use what helps you at the moment. And now we've got that X is in A union B and X is not in A intersect B. So X is an element of A union B minus A intersect B by definition of what?
set diff.
Because we put these two facts together with a set minus operator.
Mm.
By definition of set difference.
Oh, for the second one, are we gonna write the same?
Well, it's a different, look at what we're, see, remember we had cases because X was in A minus B or it was in B minus A.
So
We
is it gonna
just,
be
what should we
similar?
suppose for case two?
Suppose X is in B minus A. By
Uh-huh.
definition of set diff, we know X belongs to B and X does not belongs to A. Since X
And now I want to just stop for a minute and put a box around these to remind me I've gone as far as I can in the deconstructive mode, right? And now we got to start trying to construct to get it in here. It's like kind of we break it down so we can build it up. Now
Mhm.
what?
Since X is in B, we know X belongs to B.
You can say B union A.
B union A,
but because that's equal to A
A
union
union
B
B. Okay.
by union, okay?
Mm. And the other one is gonna be X does not belongs to A. Mm.
We don't mind so much.
And so, oh yeah, so we're back. Okay, the conclusion, yeah.
So X is an element of A union B, and X is not an element of A intersect B. So we got our conclusion, right? So X
Mm.
is an element of A union B minus A intersect B. And so what did we just show? We showed that if X is an element of A minus B union B minus A, then X is an element of A, bless you, A
Thank you,
union
sir.
B minus A intersect B. And this means, that's a definition of subset. This means that A minus B union B minus A is a subset of A union B
So
minus
if
A
this is
intersect B
the
by definition of subset. Yeah, what's that?
so if this is the second part, right? The first part when we did the inverse, right?
We did the subset inclusion. Like we just proved this direction tonight. We
And the
went
other
from
one,
here and
mm-hmm,
yeah, and this
okay,
direction was day 22.
okay. So,
It would
um,
take both to prove a set equality.
okay, so when we're proving aesthetic quality, we have to make sure we have all these on the paper.
Yeah.
Okay.
Now, let's get real. We have induction proofs, we got sequences. Holy cow, we've got sets, indexed unions and intersections and partitions. Do you really think I could give you I'm not going to give you both directions probably of anything. I'll probably give you one direction, but I might ask a question, like a simple question, like if you need to prove X equals Y, what do you need to do?
Show X subsets Y and show Y subsets X.
Mm-hmm.
Okay, that
See,
works.
that would be like reasonable. I can't, it's gonna be a time crunch test.
Can you say
Mm-hmm.
that one more time? If you said if you need to prove x equals y.
It's right here. Uh-huh. To prove X equals Y. Say it again, please, Karen.
Oh, to prove X equals Y, we have to show X subsets Y, and the second part is showing Y subsets X.
Yeah, we showed double subset inclusion, that each set is a subset of the other one, and that makes them equal. Very
Gotcha.
good. So, um, do watch the other videos, and you
Just
might like you might like the ones on Panopto better. I don't know. You can test them out. I used to always record to my computer, and then I didn't have all these different recordings with different options and different viewpoints. I think sometimes in the cloud it makes a speaker view, so when people talk and it's not me, then it kind of blanks out the page. I find that a little frustrating, but just bear with it. Everything's there that you need. We've worked all these problems now. Every single one has been worked except for maybe two part C's, which you should really work on your own so you still have something to work on.
Yeah, I just have a last question, ma'am. And you
Mm,
said we're gonna have sequences. Is it the sequence that we had on our first quiz after the other test? The sequence of where we have like numbers, then dots, dot, dot, then we have to like turn it into a formula. Is it
yeah,
that
I mean, there are
sequence?
different things I can ask you to do. There's several steps to that whole process. You know, sequences, it's a rich topic, right? Um,
Because I'm just practicing the one on the test
oh,
review, so I want to make
right.
sure
So
that
find a formula for the general term, right? And there's 3 of them on the test review, right? But on the quiz, write the summation in closed form. See, here it was just like, 1, 5, 9, 13, 17, dot, dot, dot. Or, -1, positive 1/3, -1/9, positive 1/27, -1/81, positive 1/243, dot, dot, dot. Okay. So that's, A not equal, B not equal. Okay. But in quiz 5, I was assuming you knew this skill of finding the formula. And so then I said, please write the summation in closed form, where I gave you the terms of a sequence. Like here's one. 1 plus 5 plus 25 plus 125 plus 625. Okay? So to write that as a sum, you have to be able to find A sub n. You have to, you have to use what you learned here, right? Because these are the terms of the sequence 1, 5, 25, 125, 625. It's a geometric sequence with common ratio 5. See what I mean? An initial
Mm,
term 1. So there's 2 different kind of layers of complexity. The first layer, we practice just looking at a sequence and figuring out the general term, right? What is
mm,
A sub n? What is B sub n? But now, once you learn that, then we incorporate that skill set into being able to say, oh, okay, you should start at 0, 1, 2, 3, 4, 5, to 5 of what, 5 to the K, See what I mean?
mm,
Where the first step is to realize, okay, A naught equals 1, A1 equals 5, A2 equals 25, A3 equals 125, A4. See what I mean? Like you have to kind of do that on the side. This is 5 to the
mm,
0, 5 to the 1, 5 squared, 5 cubed, right? And so I'm kind of hoping you're pretty fluent with that by now.
mm.
See, and then you just realize, okay, this is 0, 1, 2, 3, oh, 4. See, Dr. Starts at 0, ends at 4, and it's 5 to the K. Or you could
Wait,
say
why is it 4? We remove the 1? It starts at 0.
A not the first term is 5 to the 0. See?
Mm,
See, this is 5 to the 0 plus 5 to the 1 plus 5 squared plus 5 cubed plus 5 to the 4th. That's how I'm getting this formula that A sub K equals 5 to the K.
okay.
See what I mean? So there are 2 different kinds of problems, but the second kind of problem on quiz 5 requires that you understand this sort of skill set first.
Mm.
See what I mean?
Yeah, 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 I do.
Okay. And remember, there's even more problems that are uh it's not just the review, test review. There's, a big disclaimer, it's not necessarily everything, right? We've got
Oh,
quizzes, we've got special homeworks, you've got WebAssign, and there's just so many materials. Like if every week from test 2 to right now, if every week you had really spent your 8 or 9 hours every week working, then this test would be not an issue. See, that's the way that this course works. Remember, we talked about it way back at the beginning? First
yeah.
homework, when we were talking about time management. The key to being successful in a tough course is time management and not cramming, but giving it the 6, 7, 8, 9 hours a week every week so that when you do sit for the test, you're not panicking because you've done enough practice that you can kind of just pin them off.
Mm-hmm.
And you are putting in the work. Hey, Abu's joined us and he's getting the old soapbox lecture. Can't even say it. Soapbox lecture. How are you, Abu? I'm all tongue-tied. So listen, we've now worked just about every problem on the test 3 review, okay?
Oh, okay. Wasn't aware. It was I logged in at 7, but it wasn't. So I thought it started at 8, so that's why I'm only logging in now.
Oh no, I sent an email. I mean, the usual. Okay, so do you have a burning question? I'm sorry, you're a regular. Do you have a burning question?
No, it would have just been. I mean, if you went up over everything on the review sheet, then it would have been that. There was a question about on uh
We did the factorials.
yeah, I don't have too much problems.
Okay, good. And then we did the set, we did the set, subset inclusion and there's one direction is in class notes. The other direction, we did here.
Okay. So yeah, it was like I think that Fibonacci sequence.
Oh, yeah. Was it that one that was
You had
like
went over.
three? What was it? Was it the part C? Was it the one I left y'all with?
Yeah,
Let's do that one. Yeah, let's do that one for sure. Let's do that one now. It's worth it. Let me grab the, oh my gosh. I'm just looking, I've just got so much stuff open. Let me just see if I can grab that one.
I can send
Okay.
you email it.
Okay, so it's problem number 1, part C. Where is this one where C naught is 3, then minus 3/5? Is this the one you wanted or no?
It was a different one. I sent you an email about that one, but this one
When did you send me the email?
I
Like,
just did. I just did.
oh my God. Okay, hang on. Let me look at my phone. Let me look. Let me look. Oh my gosh. All right, a problem. Oh, 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 one of those. I'm not going to give you that one, I promise. Abu,
Yeah, okay.
I'm not going to give you one that hard. Okay, I'm going to just give a basic one where you have to like factor out 4 or something.
Okay.
But does anybody want to see this one?
Mm,
Yeah, I would want to see that one.
yeah, okay, yeah.
All right. So, first of all, we're just 2 things to check. Is it arithmetic or is it geometric or neither? Remember, arithmetic means to get from term to term, we are adding the same thing over and over. Are we adding the same thing over and over to get from term to term here, do you think?
No, it seems like geometric.
It seems like we're multiplying by something over and over to get to subsequent terms. Yeah, so it's geometric. What's the common ratio?
Looks like 3/5. Well,
Initial term is 3.
so it's negative. Uh, oh, 3/5. Right, 5. No, so R is 3/5, but it's negative.
And it's alternating signs too, right? So ignore the signs. Ignore the signs completely, right? We'll deal with that in a minute. What are we multiplying by to get from term to term? What do you have? What? 1/5. It's okay for the common ratio to be a fraction, right? 3 times 1/5 is 3/5. 3/5 times 1/5 is 3/25. 3/25 times 1/5 is 3/125, etc. And then you can just make it negative and it'll work out. A sub n is equal to 3 times -1/5 to the n for n greater than or equal to 0. Check the class notes, okay? And I gave you some due laters. And the other thing you can do is the ebook. This is section 5.1. Check out the exercises at the end of the ebook. A lot of them have the answers. And if you need more practice, you can get some more practice at the end of section 5.1, okay? The beauty of the formula is you can check it. Like plug in 0. -1/5 to the 0 is 1. So it's 3 times 1. Okay. C, oh, it's C. C sub n. Sorry. This should be a C. I'm not going to ever take any points off if you actually lose something like that, but it's C sub n. All right, so now plug in 1 for n. 3 times -1/5 to the 1. So it's just 3 times -1/5. Yeah, that's -3/5. Plug in a 2. 3 times -1/5 squared. Well, when you square a negative, it gets positive. When you square 1/5, you get 1/25. 3 times positive 1/25. Oh, yeah, it works. See what I mean? Like you can check your formulas. Take a stab at it and, then leave on the test to take your best stab, but then go back and check your formulas. And if you need to tweak it, you can tweak it, give yourself a little break from it and work on something else. Don't just sit there for 20 minutes, trying to do a 5-point problem, Like kind of be smart about it. All right, peeps. The old Dr. Good's got to get a rest.
Yep.
Thanks for playing.
Thanks, Professor.
Thank you,
Yeah, I'm so
Professor.
glad you showed up. All right. Talk to y'all later.
Mm.